Hello and welcome to Mobility Conversations. Our guest today is Mr. Velusamy, Global Chief of Product Development for the Automotive Sector at Mahindra and Mahindra. Mr. Velusamy, it's an absolute honor to have you with us. Welcome.
Thank you.
You've called the XUV700 your most ambitious project. Define that to us in terms of product development, engineering, and design.
The passenger car industry is all about product. You create one product, you create a company, you create a segment. The XUV500 that we have launched in 2011 had a roller coaster, and that now it's 10 years that we needed another product to replace it. The competition is very intense outside. The customers are looking always for new things. There are multiple regulations coming in, and there are paradigm shifts happening in the infotainment areas, connectivity areas.
Right.
So if you take the infotainment and connectivity areas, it's clear, the technology trend is very clear where to go, but it's not so clear where the customer is looking for in other areas. So in a way, the ambition is to find out what they are looking for, and then another way is to solve the trade-off problems so that you create a product that no one else can imagine to create at a price point that customers will drop their jaw. So that in a way, that complexity defines the ambition of this program.
From an electrical and electronics perspective, the XUV700 seems to be a significant step up from the XUV500. Could you give us more details on it?
So it's a totally new product. We conceived 3.5 years ago. It's meant to totally disrupt in every functional image target that we call it as, that matters to customer. Whether it is ride and handling, whether it is refinement, whether it is comfort, whether it is AC technology, the cooling technology, or whether it is fuel efficiency or the spirited performance, the power aspects of it, from all angles, as well as the safety. From all this perspective, the driving dynamics and the safety associated with the driving dynamics, we wanted to bring in all of the next 2 generation technologies together to a single point called XUV700. There are multiple levels of technologies have come into each area, but to pick it up, when it comes to the fundamental of this vehicle, the core is the vehicle weight and dynamics control. The moment you got that thread into your hand, you can design an SUV. SUV with a 200 km/h is not an easy job to handle the dynamics, that's handling, and the ride comfort for the rural rough road terrain. It needs a soft suspension. The dynamics at a 200 km/h needs a very stiff suspension, and the acceleration levels with 450 Nm that we are talking about needs a longitudinal stiffness of the vehicle. It's far more stiffer than any other car that we have designed so far. So therefore, we need to understand what stiffness levels that we give in the longitudinal direction and what stiffness levels that we give in the vertical direction and in the rolling of the vehicle and pitching of the vehicle. So our ability to understand this and our ability to design different systems to provide that degrees of freedom and not to provide degrees of freedom where we need bullet-like dynamic performance is the art and science together that we learned it in the dynamics. Once the dynamics comes into your hand, the handling comes into your hand without compromising the comfort of it, then what is left to you is now you bring in the safety element, because at a high dynamic performance car, you need to ensure consistently the safety so that the person who purchased the car can, without even an iota of doubt, can explore the impossible with this car. You need to remove all the doubts that he has, and you cannot express in a theory or a piece of paper. When he sits in the car, when he takes a turn, he should feel it, he or she should feel it. Oh my God, this car is planted at 175 km/h, period. That feeling, he has to get it. Then you have done your job. The physics behind is the rest, but the feeling is the first for the customer. So we decided to understand what gives this feeling. And so in search of this, we spent about a year to find it out. And we figured it out. There are 238 joineries in the vehicle that needed very critical attention to define XYZ stiffnesses differently. And we optimized those critical joints in order to give the very stiff vehicle for the longitudinal acceleration. And a vertical vibrations when it comes, that gets an isolation. When you give a vertical vibration isolation to the vehicle, you can no way compromise the longitudinal acceleration of the vehicle, because there you need very stiff vehicle to move forward, but you cannot have a stiff vehicle in the vertical direction. Second is, when you steer the vehicle, you need the response so quickly. You cannot have a lag in the steering performance. So the steering performance and the longitudinal acceleration have to be very precise. But whereas the dynamics performance of the car in a cornering, you have to be stiff in rolling. But when it comes to rough road terrain, you have to be soft. And that's the combination of the monocoque PIW design, the suspension technology, the damper technology, and the tuning of these technologies, including the tire stiffness and the tire radial and lateral stiffnesses. We spent about 1 year, 6 months only doing these tuning work, and it took enormous amount of time. The 18-inch tire will behave differently, 17-inch tire will behave differently. Different OEMs, different suppliers of tire manufacturers will behave differently, and therefore that's the task.
This is of course an all-new platform that you have introduced. So could you tell us more about the innovations that you have brought into this new platform?
So it's a brand new platform, as I said, and then we said lightweight index concept has been brought into this. It is available, it's not the new one. So you have a body weight, BIW weight, divided by the torsional stiffness of the body. So you fix the rear end of the vehicle, and then in the front suspension towers, you apply a vertical load upwards, and on the left side, you apply vertical load downwards. You try to twist the body by fixing the rear. And how much kilonewton meter that you need to rotate, Newton meter is the torque that you rotate the front end by fixing the rear end of the vehicle. And typically it is about 12 kilonewton meter per degree. 1 degree, the front axle tire moves upwards and downwards. It's about 12. This car measured value is 20. It's way above any other car. The front end is very, very stiff. So therefore when it rolls over any areas. So how did we achieve this? This is needed for longitudinal acceleration and the stiffness of the car. How did we achieve that? As I said, there are 238 joints that needed to be attended. Not only that, the BIW material selection. So you have 4 different kinds of materials. You have a standard steel, and you have a advanced high strength steel, advanced high strength steel. Then you have a boron steel. We call it as hot standard steel. material selection is one thing, and the second thing is geometry selection. So that's the second thing. Third thing is it's a sheet metal body, and you cannot have a 3 mm thickness, you cannot have it. You start with 0.65 and you add layers of 3 layers of steel. You have to join them. Now, as close as the welding joints, you get these 3 steel layers behaving in unison. Otherwise, you have steel but they are not behaving in unison. You don't get the benefit of 1.2 millimeters or 1.8 millimeters if you don't have the weldings. Not only welding, in between the layers of the 3 layer steel, you need to put a structural sealant between the weldings so that they are catching at each other, so they behave as a single unit. So we have over 6,300 weld points in this car, far above than the current outgoing predecessor model. The location and the density of the weld points are directly arrived from the CAE, where the bulk movements are noticed, and therefore you increase the number of weld points in that area and the structural sealants. For example, this car has got 155 meters of structural sealant. Never heard in this segment. 6,300 weld points. So we have chosen the boron steel. 21% the boron steel is in this car. Advanced high strength steel is in this car, that's about another 20%. The rest is between high strength steel and mild steel. With this combination, metal combination, and the geometry that I explained is the ring structure that we formed in the A pillar area, the B pillar area, the C pillar area. So you have a ring structure, and the ring structure is joined by a trident structure. So trident structure is nothing but the front long member comes, and then that splits into 3. One goes to the A pillar, the second bottom goes to the sill, and the middle goes to the door inner reinforcements. So it comes as a trident. This trident from the side, the ring in the circular are intertwined to create the structure that we want. In the floor we put hutch in, hutch out structure. So if you happen to see tomorrow when you go, you will see the PIW and you can see a hutch in, hutch out structure. Hutch is typically hutch with the ladder is typically a very strong structure for bending, and then if you introduce hutch in, hutch out, it gives bending and torsion. Beautiful. That gives the least weight but best stiffness. So there are 3 structural geometric innovations have happened in this: the hutch in, hutch out floor structure, the ring structure, the trident structure from the front to the cabin occupant. So merging together is what we created. Wherever the joineries are happening, as I said, the welding spots and the structural seals. So combination of number of welds, the structural sealant between the layers of steel, then the geometry of the steel structure and the material selection. Combining all this together, we get the lowest weight possible to get the best stiffness locally and globally. Yeah, this is exactly what we did for the BMW.
Were these developments done entirely at MRV, or was it a collaborative process among your different engineering centers?
We have used the global best experts to get to the bottom of it, but the whole simulations run in multiple places. But the core of the core simulations were done here, so that we retain that know-how.
Could you also give us a sense of the various possibilities that the XUV700 platform offers?
So this best-in-class lightweight index and high stiffness, low weight platform that gives the highest safety ratings. We will get the results, but in the internal tests we are reaching the highest safety results. On one side you get the lowest weight, and another side you get highest stiffness, and the third side you get this highest safety. So this paradox we try to solve it by using these 4 measures that we did, and that's why this is very ambitious to us, that this forms the next generation. From here the structure more or less would remain the same, but then you can modulate between the structural sealant length, the number of weld spots, the steel layer numbers, and what material that you use. But fundamentally, for near future, we have this monocoque body.
Moving into the interiors, you have obviously brought in a lot of new technological changes to the infotainment as well as the cluster. Could you give us more details on it?
So the controller is the one single controller, Qualcomm controller. It's a 6 GB RAM, 30,000 million instructions per second speed. This controller is coming from the mobile technology. You have 2 display units, and the display screen, what you see is single. So you have typically you have a display screen, then you have an air gap, and then you have a glass. So the refractive indices of these 3 objects are different. So the typical LED screens that are behind the glasses, they are very rich. But if you have to bring the same image in front of the glass, then you need to remove the air. And vacuum also you cannot keep it, because that's again a different refractive indices. So then we said we will fill in locally optically bonded adhesive, that's LOCA. That we have introduced between the screen, the digital screen, and the glass, so it brings the same refractive indices, and then you get the rich picture or the image. That's number 1. Number 2, we have the LEDs. If you calculate the number of pixels per square inch, you are coming closer to 1920. I don't remember 1920, 1970, between that. So it's a 2 HD. So it's a very rich image that comes in, because you have 1920 pixels per square inch. So the number of pixels, the quality of the image transmission that it comes to you, both brings together this long the infotainment screen that we have, and you can feed in the data from infotainment screen to cluster to infotainment, because both are 10.25. You alternately can feed in whatever data you need, because the mother controller is the single controller.
Mahindra obviously has been at the forefront of safety, and with the XUV700 you have taken the safety quotient a notch higher. Give us a sense of the thought that went into developing the safety program.
This has multiple levels of safety, as I explained. The structural safety, then the airbag in the event of unfortunate event of an accident that you deploy an airbag. You try to cover your body wherever you are, the knee, chest, head, everywhere, you side, everywhere you. And so therefore we have a 7 airbag system. Unfortunate event, you use a crash sensor. Also you use it in the side and in the front. So you have more number of crash sensors that is detecting than a regular cars. So therefore you have accurate detection, so to deploy timely airbag. So consistent and timely airbag deployment, you for sure you will do it. So that is introduced in this car. The other thing that it has is the structural design itself, that in the front end of the car is using a mild steel to absorb the first crash of 500 odd millimeters that you crash it, and then you use in the ring structure or the trident structure, you use boron steel, and the boron steel is where it is the passenger compartment, where you are absolutely do not want any millimeter deformations. After the crash of 64 km per hour, just open the door, come out. There you use boron. Like a sponge, in the event of a crash, you need to crush the sponge and absorb the crash energy. You need to allow. So that's called the crash zone or the crash tip that we are providing. So that's the design that has been done. So in terms of structural, the best car that I have explained about this weight, stiffness and crash energy absorption, and the geometry of how the loads are transmitted from the front rail to the sill to the door reinforcements to the A-pillar. So you divide it into three. Of course, the sill takes maximum energy. Then you have airbags, then you have seat belts, then you have multiple things. ABS, CSP, all this. But torque vectoring is one thing that I talked about that gives the dynamic stability control.
Mr. Velusamy, thank you very much for speaking to Mobility Outlook. It was indeed a pleasure. Thank you.
Thank you. Thank you, Devankar.